Good evening, students. Let us continue this coordination compounds. We just look at some of the problems from this chapter. Now look at this question 9.23. Give the oxidation state, d orbital occupation, and the coordination number of the central metal ion in the following complexes. Okay, there are questions asked like in this format. So what is the question? Now you have to find out the oxidation state and d orbital occupation. You have to give d orbital occupation, how many d orbitals are there in that complex, and probably how they are. I mean, sometimes you may have to give the T2G and EG configuration also. But here generally they ask the d orbital occupation. All you have to do is how many electrons are there in the d orbital and the coordination number of the central metal ion in the following complexes, and we have to choose the correct option. Okay, I mean in the exam, but here it is given. They are given complexes, and then you are asked to find out the oxidation state, d orbital occupation, and coordination number. Okay, now let us look at the first complex. The first complex is K3CO C2O4O3. Okay, the first complex is K3CO C2O4 3 times, and this one is so this one, if you look at the complex is see what is the ligand here? C2O4 3 times. It's an oxalato ligand. So the important things, you must know all the different ligands and their name and the charges. You must know this one is oxalato ligand C2O4 2 minus, actually COO minus, COO minus. That is the ligand oxalato. Cobalt C2O4 3 times they had given. So oxalato, 3 oxalato groups are there. How will you find out the charge? The charge is give me a second. So the charge is here we have to find out the charge. So what is the X? We are going to put cobalt CX, and then 3 times minus 2 oxalato. Each oxalato carries minus 2. So 3 times minus 2 is actually minus 6. And then that is equal to the overall ionic charge of it's an anionic complex. The anionic complex charge is minus 3 because K3 is there. So plus 3. So the complex ion should be charge should be minus 3. So the charge is cobalt X we put, and then oxalato, 3 oxalato there, 3 times minus 2, that is equal to X minus 6 is equal to minus 3. So when you bring the minus 3 this side, you're going to get X equal to this. So X equal to S equal to minus 3 plus 6, you will get plus 6 plus 3, I'm sorry, so plus 3. So the oxidation state of chromium in the complex is 3 plus 3. Okay, and then coordination number is Coordination number is 6 because oxalator ligand is a didentate ligand or bidentate ligand. Okay, so you can take di or bi. It's bidentate ligand. So there are 3 oxalator groups are there, and 3 times 2 is 6. So coordination number is 6. And then we'll calculate the number of d electrons. Okay, number of d electrons, cobalt, iron. I want all of you to remember, try to memorize this. Some of the things, sometimes they'll give what is it? Some questions they'll give, some questions they may not give the atomic number. So you better to memorize these transition metals atomic number, and very easy to remember. So what all I want you to do is, you have to, suppose if you remember iron, cobalt, the first transition element, actually 3D series. Okay, the 3D series, what are the elements present? Actually, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Okay, so these are the 10 elements. Okay, now if you look at the last class itself, I discussed. Okay, if you look at the scandium atomic number, actually it's 22, and then 21, scandium 21, 22, and then we have vanadium 23, 24 chromium, 24, and then chromium 25, then iron 26, iron 26, cobalt 27. It's better memorize this, and it is easy. Cobalt 27, and then you have nickel 28, copper 29, and then zinc 30. Okay, zinc 30. Now let me give some space. I need some space. So while I type itself, you can just memorize scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel. So it is good to learn this atomic number, mass number, and the electronic configuration, because it will be useful in many questions. Okay. Now this one already I told you, the 21. What you have to do is, how do you write the configuration? Actually 4s2 3d1. That is that 21. 2 goes to 4s orbital, and then 1 goes to d orbital. Okay. So just memorize that. So 4s2 3d1. 4s2 3d1 is the configuration of scandium. 4s2 3d1. 4s2 3d1. 21 2 1. 2 goes to 4s orbital. 1 goes to 3d orbital. Okay. Now next, you just go for the titanium. Titanium, the configuration, same thing. 22 4s2 3d2. And then vanadium 4s2 3d3. And then chromium, there is going to be change. Big 4s, it should be 4s2 3d4, but 3d orbital is going to borrow an electron from 4s and becomes 3d5 and 4s1, because both the orbital, by doing this, both the s orbital and d orbital becomes half filled. So I'm going to just give this one a different color, so that so that you remember chromium is chromium, and then copper behaves differently. Okay, I put it as dark, bold letters. And then manganese, no change. 25, 4s2, 3d5. Okay, 3d5, total number of electrons in the valence shell, you can just add. For scandium, 2 plus 1, 3. Titanium, 22, 2 plus 2, 4. So 2 from s orbital, 2 from d orbital. So and so. You can just memorize. Why? It's very important that you need to know this one. So 26 for iron, 26. So it's going to be 4s2, 3d6. 4s2, 3d6. Cobalt 27, 4s2, 3d7. And then nickel 4s2, 3d8. Copper 4s2, 3d9. It should come, but again, just like chromium, it is going to borrow an electron from s orbital and become 4s1, 3d10. Okay, so again, I'm going to write this one as in red. Okay, so copper and chromium behaves differently. Okay, because their configuration is so just remember chromium copper is going to behave slightly different, this electronic configuration from this rule, and chromium is going to behave differently from this rule. So I just want to carefully listen. Just memorize this one, scandium to zinc. This is the electronic configuration. Okay, and then from this one you can very easily draw the or write the ionic electronic configuration. For example, scandium 3 plus. So already it has 3 electrons in the valence shell. Remove all the 3, so it becomes what? No electrons in the valence shell. 4s0, 3d0. And titanium 22, 4s2, 3d2. Titanium 3 plus. So it will become, remove 3, you will get only 3d1 configuration. So titanium has 3d1 configuration. Some of the things, if you memorize, it is very good for you. So directly you can, it will save times. What is, sir, why I should do it? Can I just calculate all of them? Yeah, you can calculate, but the problem is you will be wasting time. So time is also very important, time management. So if you remember, you try to memorize, this is very easy. Titanium 22 and then remove 22. If you remove, there are 4 electrons in the out, 2 plus 2. Okay, so 2 plus 2, 4. Titanium 3, remove the 4 electrons, become only 1. So 3d1. Scandium 21. So 2 plus 1, 3. Minus 3, 0. Okay, so d0. Yes, scandium is d0. It is d0. Scandium is d0. Titanium is d1. And then and vanadium 23, 4s2, 3d3, and then vanadium 3 plus, it becomes 3 plus 2 plus 3, 5 minus 3 becomes what? 2. So d1, vanadium 3 plus, because the general oxidation state of 3d series, first transition series is like it has +2 and +3 also there. Okay, so of course there are so many variable valencies. Iron has +2, +3, nickel has +2, generally +2 only, cobalt +3. And then chromium, it has variable valency, manganese has variable valency, copper +1 and +2, zinc only +2. So remember those things. And then let's say chromium 3 plus, Chromium 3 plus has chromium 3 plus. So 24 minus 3 to 6 minus 3, 3. So the number of d electrons 3. So if you know the order, we can very easily find out. So chromium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So 0, 1, 2, 3. You can see first one scandium 0. You can just remember for scandium 0, 3 plus, of course. If it is 2 plus or 4 plus, accordingly you have to add or subtract. But if you know the 3 plus, we can easily calculate. Okay, 3 plus 24, and then manganese. Manganese generally there is no 3 plus is there, but the common state is plus 2. Manganese 2 plus is D5. If it is 3 plus, manganese 3 plus, it's going to be 4. Okay, manganese 3 plus. I'm going to just write here Mn 3 plus. So Mn 3 plus ion. This is how you are going to calculate. Okay, this one is 4. And then iron. Another one is iron. Iron is iron Fe3 plus becomes Fe2 plus iron 26, students. Iron 26. 26 means so how many electrons are there? 6 plus 2. 8 electrons are there. If it is Fe2 plus, there are 6. In Fe3 plus, it is going to be D5. Okay, D5. And then look at cobalt 27. 27 minus 3 CO3 plus. 27, 3 means it becomes D6. Cobalt 3 plus is D6. Nickel 28. 28 means 10 electrons, 4s2, 3d8. So remove nickel 3 plus. Nickel 3 plus means it's going to be 3d7. Okay. So the common oxidation state of nickel is 2. Okay. So if you go to the end of the first D transition series, the low oxidation states are going to be stable because of the inert pair effect. Okay, because that s electrons, they don't want to take part in the bonding, so they don't generally, they try to just stay as a lower oxidation state. Keep that in mind. And then copper, there's 3 plus there. Okay, copper, it's going to be +1 or +2. There is no 3 plus, remember that one. So I'm going to just leave here. So remember this. So cobalt 3 plus, if you remember just cobalt, all you have to do is cobalt. If you know here what they have asked is, they asked to find out the oxidation state, they have asked d orbital occupation, they have asked coordination number, they have asked. So we calculated the oxidation number and calculated the coordination number, and then number of d electrons based on the ion d configuration. We can say that number of d electrons, and also we can say whether it is all the electrons are paired, whether we can say diamagnetic or paramagnetic. All those things we will be able to tell that one. Okay, so here they have asked how many d orbitals are there in cobalt 3 plus. Cobalt 3 plus, I said cobalt, immediately you should think 27. That is cobalt atom atomic number. So the configuration is 4s2, 3d7, 2, 7. 3d7, and then 3 plus means remove 3 electron, it becomes 9 minus 3, 6. So d6. Okay, so d6, if the weak ligands, generally if it is weak ligands, you will form, like, listen, if it is a weak ligand, last class I discussed, or sometimes I discussed that if it is a weak ligand, it's going to form outer complex. It means the 3d orbitals will not be touched, so it is going to use the 4d orbitals. Okay, so the 3d orbit weak ligands form high spin complexes. So how are you going to arrange this d6? How are you going to arrange the d6? We are going to arrange all the 5 orbitals, d orbitals, 1 electron, and then the first d orbital going to get 2. So you will get 4 unpaired electrons in high spin complex. If it is a low spin complex, if the ligand is a strong ligand, these 6 orbitals going to be paired, and you are going to get all electrons are paired, and then you will get low spin complex. Okay. And then next to look at this complex. It says, this is says CR EN2, CR EN2, and then Cl2 complex plus, and then Cl minus, it is given CR En twice Cl2. The overall charge is plus, it's a cationic complex, and then Cl minus is the counter ion. Now find out the oxidation state. The oxidation state here we have chloride ion is an anion. There are 2 anions are there. So 2 into -1 -2. En, ethylene diamine, or ethane 1,2-diamine is a neutral ligand. And then it get 0. So x plus 0 minus 2 equal to plus 1. The overall charge is plus 1. Why plus 1? Because Cl, that is out counter ion is only Cl minus, so it has to be plus 1. So it is plus 1. So what you give, what is the oxidation state? Now -2, when it comes to the next other side, it becomes plus minus plus 1, plus 2, you will get the oxidation state as x equal to plus 1, and then plus 2, you will get plus 3. So oxidation state of chromium is in this complex is plus 3, and then coordination number is 6, of course. Coordination number is 6, students, because En is a didentate. So there are 2 didentate ligands, means 2 into 2, 4, plus 2 chloride ions. So total 6. Coordination number is 6. And then Cr3 plus 3. Cr plus 3 means just now we saw Cr chromium of what is the electronic configuration? Chromium is 24. It is 4 is 1, 3d 5. So 24. 6 electrons are there. Remove 3 electrons, then you get remaining 3 electrons. It is actually D3 configuration. So basically, chromium 3 plus is a D3 configuration. So since it is D3, since it is a D3 configuration, it is going to be whether whatever it is, complex it forms. If it is D3 means the last 2 d orbitals are available, it is going to use the inner orbital, but still it is going to be paramagnetic, because the 3 d orbitals are I mean, it has only 3 electrons. The 3 electrons are going to occupy each of the d orbitals. Remaining 2 orbitals are going to be empty. That d orbital is going to be used for complex formation. So it is a paramagnetic complex. Okay. Next, they had given next they are given, you have to find out NH4 twice COF4. Okay, NH4 twice COF4. Now it is a coordination number 4, because cobalt oxidation state. Look at the oxidation state of cobalt. You will have ammonia. 2 ammonia ions are there. Positive ions are there. 2. So the complex ion should be plus -2. So we have cobalt X. And F, fluoride ligand has -1, so 4 into -1 -4. The overall charge of the complex is -2. So x equal to -2, and then plus 4 equal to plus 2. The oxidation state of cobalt here is cobalt 2. And then coordination number is 4 because we have the complex contains only 4 ligands. So coordination number is 4. And then cobalt 2 plus. Remember cobalt 2 plus. Now we saw cobalt. What is the cobalt atomic number? 27 atom. Okay, and 27 minus 2, you will have 7 d electrons in the CO2 plus ion. Okay, so D should be D7 students. Okay, cobalt 27, 27. In that 27, 2 plus 7, 2 plus 7, 9 electrons are there. From the 9 electron, we are going to remove 2 electrons to become CO2 plus. CO2 plus is a D7 ion. And D7 ion, how can you arrange the D7 ion? You can basically arrange it as, I'm going to show you here. How can you arrange it? Give me a second. So we are going to arrange it as so D7 is equal to, so what we are going to do is we are going to arrange the D7 as so first orbital 2, and then again we are going to basically we are going to put 5 orbitals 1 1, and then we are going to put the next one. Okay, this is what D7, how is it? What, 2 plus 2 plus 4, 2 plus 2, 4 plus 3, 7. This is how the D7 configuration is going to be there. And F minus is a weak ligand. So even if it is a coordination number is 4. 4 means either it can form a tetrahedral complex or square planar complex. Okay, square planar complex. So what are the orbitals we need? dsp2. Okay, square planar dsp2. 1 d orbital it needs. So even if suppose if it is a inner d orbital, then what you have to do is this: you have to put, there are 3 unpaired electrons that you have to pair one, and still you will get 1 unpaired electron. Understand? But if it is a tetrahedral complex involves sp3 hybridization. So in this sp3 hybridization, you will have 3 unpaired electrons. You will be still, it will be paramagnetic, or they call it as, sometimes they call it as weakly paramagnetic, strongly paramagnetic. Okay, if weakly paramagnetic, it will have minimum number of unpaired electrons. So strongly paramagnetic means it will have more number of unpaired electrons in the complex. Okay, now next one, the complex they have given is MnH2O 6 times and then 2 plus SO4 2 minus. Here aqua complex is an aqua ligand is water. It's an aqua ligand and it is a neutral ligand. So you will have the charge of the complex becomes charge of the metal ion. So what you get is x plus 0 is equal to plus 2. So the oxidation state of Mn is Mn is actually x equal to 2. X equal to plus 2, and then coordination number is 6 because 6 aqua complexes are there. I mean aqua ligands are there, so it is 6. And then Mn2 plus. Okay, what is the atomic number of manganese? So 25. 25. So Mn2 plus, it is a D5 case. There are T5 d electrons are there, and our water is depends. So now 5d again here, what is it? We have D5 configuration. How will you arrange the D5? How will you arrange the D5? So we are going to D5 means generally 1 electron in all the 5 orbitals. Okay, if it is a strong field, I mean weak field. If it is a weak field, you get all the 5 electrons are not paired, unpaired. But if it is a strong field, so you are going to get the 5 electrons become paired. So 2 will be paired, and then one unpaired electron will be there. Okay. Next one. Now look at this one. Write down the IUPAC name for for each of the following complexes and indicate the oxidation state, electronic configuration, and coordination number. Also give the stereochemistry and magnetic moment of the complex. Okay. So what we have to do is we have to, just like the previous one, we have to name, we have to IUPAC name we have to give, and oxidation state, electronic configuration of the metal ion we have to give, and coordination number. And also we were asked to give the stereochemistry of the complex along with magnetic moment. Okay. Now let us discuss here. Now the first one is KCr H2O twice, C2O4 twice. Okay. Now dot. Okay, I'm going to put a dot here. Okay, there is a dot there. The dot indicates it is a hydrate. Okay, whenever there is a dot there, it means it is a hydrate. Okay, so what is the IUPAC name for this complex? So find out the cation and anion. What is the cation here? K potassium. And then what is the anion? The complex Cr H2O twice, C2O4 twice. So you know that according naming, we have to use them according to the alphabetical order. So we put the cation first, potassium, leave space, and then we are going to name it as diaqua, because the alphabet starts with A, diaqua, and then dioxylator. Okay, so there are 2 oxalate groups. So dioxylator, chromate, because it is an anionic complex, chromate. The oxidation state is oxidation state is 3. Oxidation state is 3. We just calculated above. How, sir? Here you see chromium H2O is a neutral complex, so 0 charge. And C2O4, there are 2 C2O4 are there. Each one of C2O4 carries 2 minus. So 4 minus there. And then look at the H. What is the overall complex charge? Minus 1 minus, because only 1K is outside. Counter ion is 1K. So the anionic charge should be 1 minus. So here 4 minus there. So 4 minus, if you bring it the other side, it becomes plus 4. So minus 1 plus 4, you get plus 3. So here it is calculated there. So x equal to, no, that is equal to x minus 4 equal to minus 1. So x equal to minus 1 plus 4 equal to plus 3. Okay, that is the oxidation state of chromium here. And they have asked about the coordination number 6, and it is octahedral shape, electronic configuration. Look at this, is what I said, even though they had given in this stage. So what you have to do, Cr3 plus, chromium 3 plus, chromium 3 plus. Okay, remember scandium, titanium, vanadium, chromium, manganese. I said scandium. I told D configuration. Scandium, vanadium, scandium, titanium, vanadium, chromium, manganese. If you remember that, 3 plus, you can easily scandium 0, titanium 1, vanadium 2, chromium 3, D3. Directly sum up the thing, you can just put it if you know the trick, if you memorize the trick. Okay, so it is chromium 3 plus is 3D3. Okay, so 3D3, how can you arrange this 3D3 in terms of T2G and EG? Okay, how can you put this one? So we are going to put, there are three 2Tg level. Remember in crystal field theory we saw. So each of them are going to occupy 1, 1, 1. Okay. So octahedral, in octahedral splitting, you remember the T2G level is going to be below the barycenter and then above EG levels will be there. Okay. So EG will have no electrons. So EG 0. Okay, this is the electronic configuration in terms of crystal field splitting. 3D3, this is how you should write. Yes, okay. Now I told you 3D3, whether it is weak field, strong field, 3D3 is same because only three electrons are there. These 3 electrons are going to occupy D2G level. Okay. Now, then magnetic moment. Okay, magnetic moment mu equal to the formula last time we saw. It's going to be square root of 3 into square root of n into n plus square root of n into n plus 2. This is what we saw last time. Okay, so that is equal to square root of number of unpaired electrons equal to 3 and 3 plus 2 5. So 3 into 5. So that is equal to, I already asked you to memorize, if 3 electrons are there, the magnetic moment is going to be what? 3.9 or 3.8, close to 4. That's what I taught last time. So 3 into 5, square root of 15. Square root of 15 is equal to 3 so it's 3.87 Bohr magneton, BM. Okay, so this is the magnetic moment. How you do is, so problems will be asked to match the Bohr Bohr momentum, or they may ask to the electronic configuration. You have to choose the electronic configuration correctly, or oxidation state. These are all, some of them are easy, some are difficult. If you know, only thing is timings. The timing is important. So if you know, if you calculate quickly the electronic configuration, so you can save lots of time. So okay, do that one. And the next one is, let us do some other problem. And sometimes stability of complexes, they may ask if there is more number of bidentate ligands, that complex will be more stable compared to unidentate ligands. Okay. Now let us look at 9.29. Which among the following has highest magnetic moment value? Which among the following has highest magnetic moment value? Okay, so in order to calculate the magnetic moment, we need to know the atomic number and then electronic configuration, basically electronic configuration of the ion. And then we need to know how many unpaired electrons are there based on the strong field or weak field. And then from the unpaired number of unpaired electrons, then we have to calculate the magnetic moment. Okay, so here, which has the highest magnetic moment? So first one is chromium H2O6 3 plus. Okay, all of them same ligand. So H2O you can consider it as a weak ligand because I told you the other day, if the donor atoms are fluorine halides, if they are halogens, if they are oxygen, and if they are sulfur, they are weak ligands. Okay, and if the donor atoms are nitrogen, carbon, phosphorus, generally they are strong field. Okay, now look at the electronic configuration 3. So just now we learned the chromium 3 plus is 3D3, and then Fe2 plus, we know Fe3 plus is 3D5, Fe2 plus should be 3D6. Now just remember is 3D2 plus is 3D, I mean iron is 3D6. How, sir? 3D iron atomic number, what is it? It's 26. So 2 plus 6, 8 electrons are there. We are going to remove 2 electrons, and so you get 3D6 configuration. So 3D6 and zinc வந்து 3D10. Zinc நல்லா கண்ணமூடிட்டு ஞாபகம் வச்சுக்கோங்க. It is the last element of the first 3D series. Last element, its configuration is 3D10, completely filled. D electrons are completely filled, and they are actually does not come, even though they are placed in the D block elements. They are not called D block elements because D block elements should have unfilled D orbital. Okay, so it has a completely filled D orbital. So number of D electrons are 10. Okay, 3D10. Okay, so Fe2 plus in H2O is a weak complex, so it is going to be high spin, means unpaired electrons should be there. So Fe2 plus 3D6. Last time we saw here for that other one. I'm just going to copy that here. So let me just copy this. So I'm going to put for here. Okay, so let's see here. This is 3D6. So I have first D orbital, 2 electrons, second one, 1 1 1, the remaining 4 1 1 there. And then if you have here, if it is D3, zero, and then 0, nothing, empty. D3. Okay. Now, suppose how do you write this in terms of crystal field splitting configuration? This how you have to write. You have to write T2G. Okay, T2G. It's a weak complex. Okay, so T2G. We are going to have how many? 6. We are going to fill the 6 electrons. Okay, since it is, there are 3 orbitals are there, we are going to, actually 5 are there. So 5 are there, weak figure. If it is a weak field, all the 5 should get 1 1 each, and then pairing. So in T2G, where there are 3 orbitals are there, in that 3, what happens? The first one is paired, and second one is 1 electron, and next one is 1 electron. So there are 4 electrons are there in the T2 level. And then in the EG level, we have 2 orbitals are there. Each of them will have 2 2. Okay, so each of them will have 2 2. So you will put 4 in the T2G level and 2 in the EG level. 4 in the T2G level and 4 in the EG level. So you will get this is the configurations, crystal field configuration for this one. Okay, now calculate the magnetic moment. Same thing, n into n plus 2, n into n plus 2. So how many electrons are there? 4 unpaired electrons are there. So the magnetic moment will be 4 plus 2, 6. So 4 plus 2 is 6. So 4 into 6, you get 24. Square root of 24. That is equal to square root of 25. What is the closest perfect square? 25. 5 are 25. Here it is very close to 25. So 4.9 bm. Okay, so now look at the electronic configuration of zinc 2 plus. Zinc 2 plus actually 3D10. There can be no unpaired electron. So all are paired electrons. So among these three, we have the maximum number of unpaired electrons will be in Fe2 plus. The highest magnetic moment will have FeH2O 6 2 plus. Okay, hexa-aquo ferrous, hexa-aquo iron 2 complex. Hexa-aquo iron 2 complex will have the maximum number of highest value of magnetic moment. This is what I said. Look at this question. Amongst the following, the most stable complex is hexa-aquo iron and the hexaamine iron 3. Okay, and then here trioxalato ferrate, trioxalato ferrate 3, and hexachloroferrate. Okay, so in this one, which of them will be most stable? As I said, if it is a didentate ligand or polydentate ligand, that complex will be more stable. If aqua is a monodentate ligand, ammonia is a monodentate ligand, or unidentate ligand, Cl minus is a unidentate ligand. But oxalato is a bidentate ligand or didentate ligand. It is a it's going to form a ring, so that the structure is going to be stable. Okay. Now I'm going to stop here. Now look at here. Correct. Wavelength of absorption. I think we saw a similar similar problem last time. Okay, wavelength of absorption means if there has to be what is it? There has to be unpaired electron, d electron should be there, and whichever is a weak ligand. If it is a weak ligand, it's going to be the wavelength of that weak ligand is going to be more compared to the strong ligand. Okay. So, okay, students, I'll stop here.